Hello there, and welcome to the Palette Explainer. Tonight, we'll descend into the quiet, mysterious, and otherworldly world of the deep sea. The ocean is perhaps the most ancient and patient mystery on our planet, a vast expanse of blue-black silence that stretches farther than any horizon we can see, deeper than any mountain is tall, and darker than any night sky. More than 70% of Earth's surface lies beneath these waters, yet we have explored only a fraction of what rests below. The deep sea is a realm untouched by sunlight, a place where pressure crushes and cold numbs, where time moves differently, and life takes on forms that seem borrowed from dreams. It is a world that existed long before us and will endure long after, holding its secrets close, revealing them only in whispers to those patient enough to listen. Tonight we will let ourselves drift through these depths, not as explorers rushing to discover, but as quiet visitors content to simply observe and wonder. We will encounter strange lights in the darkness, hear echoes of sounds that travel for thousands of miles, and glimpse creatures that defy our understanding of what life can be. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, allow yourself to drift. Let your breath slow, your shoulders loosen, and let the darkness of the ocean cradle your senses as you prepare for rest. Let's begin. Deep below the waves, there are places where a peculiar humming fills the water, a low-frequency vibration that seems to come from nowhere and everywhere at once, resonating through the cold currents like the breath of something vast and unseen. Scientists first detected these hums using underwater listening devices, sensitive instruments dropped into the abyss to monitor the ocean's acoustic landscape. And what they found was unexpected: a steady, rhythmic sound that pulses at intervals too regular to be random, yet too irregular to be mechanical. The hum rises and falls, sometimes louder, sometimes softer, as if the ocean itself were breathing in its sleep. Researchers have proposed many explanations over the years, some suggesting the sound comes from geological activity deep within the Earth's crust, the grinding of tectonic plates or the rumble of underwater volcanoes preparing to wake, while others believe it may be biological in origin, perhaps the collective songs of countless creatures communicating across vast distances in frequencies we are only beginning to understand. The hum continues, night and day, a constant presence in the deep, a reminder that the ocean is never truly silent, that even in its darkest corners there is always something listening, always something singing.
In the endless black of the abyss, there exists a phenomenon known as the deep scattering layer, a mysterious zone that appears on sonar readings as a false seafloor, a phantom bottom that rises and falls with the rhythm of day and night. Early sailors and oceanographers were baffled by this moving barrier, this layer of something that reflected sound waves so strongly it seemed solid. Yet when they lowered their instruments through it, they found only water and the soft, drifting bodies of countless small creatures. The deep scattering layer, it turned out, is made of life. Millions upon millions of tiny fish, squid, jellyfish, and crustaceans that migrate vertically through the water column each day in what is perhaps the largest animal migration on Earth. As daylight fades above, these creatures rise from the depths to feed in the relatively rich waters near the surface, And as dawn approaches, they descend again into darkness, seeking refuge from predators in the cold, lightless depths. This daily journey spans hundreds of meters, a commute undertaken by so many organisms that together they create a living, breathing layer dense enough to fool sonar, a collective presence so vast it moves like a single entity, rising and falling with a rhythm older than memory.
Certain abyssal zones whisper of strange lights that flicker in patterns too complex to be mere bioluminescence, displaying sequences and symmetries that suggest intention, perhaps even communication. Deep-sea cameras deployed in these regions have captured brief flashes and glows that appear, pulse in intricate arrangements, and then vanish, leaving researchers to wonder what they have witnessed. Most bioluminescent creatures use their light for simple purposes, to attract prey, to startle predators, to find mates in the darkness. But these patterns seem different, more elaborate, as if they were writing messages in light across the canvas of the deep. Some scientists speculate that these displays might be the visual language of species we have not yet identified, creatures intelligent enough to have developed complex systems of signaling, while others suggest the patterns could be caused by unusual concentrations of bioluminescent plankton responding to currents in ways that create the illusion of deliberate design. The truth remains elusive, hidden in depths that cameras can visit only briefly before their batteries fade and they must return to the surface, leaving the lights to pulse and fade in the darkness, unseen and unexplained.
There are ocean depths where enormous, perfectly circular depressions mark the seafloor, vast craters arranged in patterns that seem almost geometric, too regular to be the random work of erosion or volcanic activity. These formations were discovered relatively recently, revealed by high-resolution sonar mapping that can peer through miles of water to create detailed images of the bottom. And what these images showed surprised everyone who studied them. The circles measured dozens of meters across, their edges raised slightly like the rims of ancient impact sites, their centers smooth and barren. They appear in groups, sometimes arranged in lines, sometimes in clusters, as if following some hidden logic or pattern. Researchers have proposed that these depressions might be created by deep-sea currents swirling in vortices strong enough to scour the sediment away. Or perhaps they are the nesting sites of some large unknown creature that clears the seafloor in preparation for laying eggs, much like certain fish create circles in shallow water. Others wonder if they might be the traces of geological processes we don't yet understand, events that happen only in the deepest places where pressure and chemistry create conditions unlike anywhere else on Earth. The circles remain, silent and patient, waiting for us to understand their purpose.
A few underwater realms reveal the presence of what oceanographers call ooze, deep accumulations of sediment so fine and so soft that it behaves almost like a liquid. A thick, viscous layer that blankets the seafloor in some regions and swallows everything that falls into it. This ooze is made of the remains of countless tiny organisms, the shells and skeletons of plankton and other microscopic life that have drifted down from the sunlit surface waters over millions of years, settling grain by grain to form layers hundreds of meters thick. It is a graveyard and a record, a chronicle written in calcium and silica, preserving evidence of ancient climates, extinct species, and events long forgotten. But the ooze holds mysteries too, for within its depths, strange pockets of activity occur, places where methane bubbles rise and bacteria thrive in the absence of oxygen, creating microenvironments that support life in ways that challenge our understanding of what is possible. Some of these pockets generate enough heat through chemical reactions to warm the surrounding sediment, creating thermal oases in the cold abyss where unusual organisms gather and survive. The ooze shifts and settles, slowly, infinitely slowly, and within its soft embrace, the deep sea keeps its secrets. Scientists have long wondered why certain regions of the ocean floor emit faint but persistent clouds of particles that drift upward like smoke, rising from vents or cracks in the crust that seem to have no obvious source of heat or volcanic activity. These particle clouds were first observed by submersibles exploring remote trenches, their lights catching the swirling streams of matter suspended in the water, and the pilots initially assumed they had found hydrothermal vents, the hot springs of the deep sea where mineral-rich water pours from the Earth's interior. But when they took measurements, they found the water was not hot. It was cold, or only slightly warmer than the surrounding ocean, and the particles were not the metallic sulfides typically associated with volcanic activity. Instead, the clouds seemed to contain organic matter, fragments of biological material rising from the sediment, as if something beneath were disturbing the bottom, churning the ooze and releasing the accumulated remains of ancient life. Some researchers propose that these cold seeps are caused by the slow release of trapped gases, methane or carbon dioxide escaping from deposits buried deep beneath the seafloor, while others suggest that unknown organisms might be responsible, creatures that burrow through the sediment and create the disturbances we observe. The clouds continue to rise, day after day, year after year, their origin a quiet enigma.
Hidden far beneath the surface lies a formation that defies easy explanation, a massive stone structure that rises from the abyssal plain like a monument. Its surface is smooth and angular in ways that erosion alone seems unlikely to produce. Discovered during a mapping expedition, this formation stands hundreds of meters tall, a solitary pillar in a landscape otherwise flat and featureless, and its presence has sparked considerable debate among geologists and oceanographers. The angles of its faces, the sharp edges where planes of rock meet, suggest deliberate shaping, yet no natural process known to science readily accounts for such geometry at these depths. Some scientists argue that the structure is a remnant of ancient volcanic activity, a plug of hardened magma that remains standing after the softer surrounding rock eroded away over millions of years, while others wonder if tectonic forces might have fractured and tilted layers of stone in unusual ways, creating the illusion of construction. A few more speculative voices have asked whether it could be evidence of something else entirely, perhaps a relic from a time before recorded history, though such ideas remain firmly in the realm of hypothesis rather than accepted theory. The formation stands in darkness, encrusted with deep-sea life, a mystery carved in stone.
In the dark quiet of the ocean floor, something unusual occurs in certain trenches where the pressure is so immense that water itself behaves differently, becoming denser and heavier, almost viscous, creating a boundary layer that separates the deepest water from the layers above. This extreme environment should be inhospitable to all but the most specialized life forms, yet explorers have found thriving communities here, creatures not just surviving, but flourishing in conditions that would crush and suffocate most organisms on Earth. These deep trench inhabitants include fish with bodies so gelatinous they seem barely solid, crustaceans with exoskeletons adapted to withstand pressure that would collapse steel, and microbes that draw energy from chemical reactions rather than sunlight or oxygen. But the mystery deepens when researchers examine the genetics of these creatures and find evolutionary lineages that are surprisingly ancient and surprisingly isolated, suggesting that life in these trenches has been cut off from the rest of the ocean for vast spans of time, evolving independently in these pockets of extreme darkness. How these populations originated, how they reached the deepest places on Earth, and how they maintain genetic diversity despite their isolation are questions that continue to puzzle scientists who study them. Questions wrapped in the immense pressure and cold of the deepest seas.
Drifting in the silent blue, one may encounter the remains of massive whale falls, the bodies of great whales that have died and sunk to the ocean floor, where they create temporary oases of abundance in an otherwise nutrient-poor environment. A single whale carcass can weigh dozens of tons, and as it descends through the water column, it carries with it a feast that will sustain deep-sea life for years or even decades. First come the scavengers, the sleeper sharks that tear away flesh with slow, powerful bites, the hagfish that burrow into the body and consume it from within. And then come the specialists, creatures that feed on the bones themselves, extracting the lipids and marrow trapped inside. Among these specialists are zombie worms, strange segmented animals without mouths or stomachs that use root-like structures to penetrate bone and absorb its nutrients through symbiotic bacteria living in their tissues. But the mystery of whale falls extends beyond the creatures that consume them, for scientists have found that these sunken bodies serve as stepping stones for deep-sea species, allowing organisms that cannot survive in open water to migrate between hydrothermal vents and cold seeps by hopping from one carcass to another across the vast, empty plains of the abyss. The fallen whales become islands, temporary but vital, and their role in connecting distant ecosystems is still being explored and understood.
Some deep-sea regions hold concentrations of heavy metals and rare minerals in forms and quantities that seem anomalous, creating patches of seafloor where the sediment glitters with manganese, cobalt, and other elements, in nodules and crusts that grow slowly over millions of years. These formations, known as polymetallic nodules, look like dark potatoes scattered across the ocean floor, and they form through chemical processes that concentrate metals from seawater, precipitating them layer by microscopic layer around a nucleus, a shell fragment, a shark tooth, a piece of bone. The nodules can grow to the size of grapefruits or larger, and they cover vast areas of the abyssal plains, particularly in the Pacific Ocean, where they lie untouched in the deep darkness. What makes them mysterious is not just their composition, but the environment they create, for their surfaces become habitats for sponges, corals, and other sessile organisms that cannot attach to the soft sediment but need hard substrate to anchor themselves. Removing these nodules, as some have proposed for mining operations, would destroy these habitats, but it would also remove features that took millions of years to form, raising questions about the balance between human need and the preservation of deep-sea ecosystems we are only beginning to understand. The nodules rest in the darkness, accumulating metal and mystery in equal measure.
Explorers have reported traces of massive underwater avalanches, vast cascades of sediment that periodically thunder down the continental slopes, carrying millions of tons of material from the shallows into the abyss, in events that reshape the seafloor and bury everything in their path. These turbidity currents, as they are called, are triggered by earthquakes, storms, or the simple accumulation of sediment that becomes unstable and collapses under its own weight. And when they occur, they move with surprising speed, flowing like muddy rivers through the deep ocean and carving channels and canyons into the underwater landscape. The evidence of these events is written in the geology of the seafloor, in the layered deposits they leave behind, but witnessing one is exceedingly rare, and understanding their full impact on deep-sea ecosystems remains incomplete. Some researchers believe that these avalanches may transport organic material from coastal waters into the deep sea, providing sudden influxes of nutrients to organisms starved for food in the otherwise barren abyss,
while others worry that the currents might damage delicate habitats like coral gardens and sponge fields, burying them under meters of sediment from which they cannot recover. The ocean floor is not as stable as we once imagined, not as unchanging, and the currents that flow across it in darkness are powerful and relentless.
Far below, in the crushing pressure, something mysterious unfolds around hydrothermal vents, those volcanic springs where superheated water pours from cracks in the Earth's crust, carrying dissolved minerals that precipitate out as the water cools, building chimneys and towers of stone that can grow meters tall. These vents were once thought to be barren, hostile places where nothing could survive. But when scientists first visited them in submersibles, they found ecosystems teeming with life. Communities built not on sunlight and photosynthesis, but on chemosynthesis, the process by which bacteria convert chemicals from the vent water into energy. Around these vents live tube worms with blood-red plumes that can grow longer than a human is tall, clams and mussels with shells as large as dinner plates, and crabs so densely packed they carpet the rocks. But the mystery extends beyond the presence of life itself, for genetic studies have revealed that vent organisms share ancestry with creatures living thousands of miles away at other vents, despite the vast distances of empty ocean between them. How these species dispersed, how their larvae traveled from one isolated vent field to another, crossing barriers that should be insurmountable, is a puzzle that scientists are still working to solve. The vents glow and shimmer with heat, their chemistry alien, their ecosystems improbable, their existence a reminder that life finds a way even in the most unexpected places.
In the quiet waters above certain seamounts, researchers have detected unusual magnetic anomalies, variations in the Earth's magnetic field that suggest the presence of large deposits of magnetic minerals or perhaps ancient lava flows frozen in configurations that preserve magnetic signatures from millions of years ago. Seamounts are underwater mountains, volcanoes that rise from the seafloor but do not break the surface, and they are scattered throughout the ocean basins like hidden peaks in a submerged mountain range. Many seamounts are geologically old, extinct volcanoes whose fires have long since cooled, but they continue to influence ocean currents and marine life, creating upwelling zones where nutrients are brought to the surface, attracting fish, whales, and seabirds. The magnetic anomalies associated with some seamounts are strong enough to affect compass readings on ships passing overhead, and in earlier centuries, sailors sometimes reported strange navigational discrepancies in these areas, deviations they could not explain. Today, scientists study these anomalies to learn about the history of Earth's magnetic field, which has reversed many times over geological history, flipping north and south in ways that are recorded in volcanic rocks. But the seamounts themselves remain largely unexplored, their slopes and summits visited only briefly by remotely operated vehicles, their full stories still hidden beneath the waves.
Long ago, researchers detected hints of a deep-sea current that flows in the opposite direction to what models predict. A slow but persistent movement of water that seems to defy the expected circulation patterns of the ocean. This countercurrent was discovered through careful analysis of temperature and salinity data collected over decades, measurements taken from ships and floats drifting in the deep. And when scientists plotted this data, they found a stream of water moving against the prevailing flow, traveling from east to west where it should be moving west to east, or vice versa. The cause of this anomaly is not entirely clear, though theories abound. Some suggest that the current might be driven by subtle differences in water density, gradients so slight that they are easily overlooked, but sufficient to push vast volumes of water in unexpected directions over time. Others propose that underwater topography, ridges, trenches, and seamounts, might channel the water in ways that create these counterflows, guiding the current along paths determined by the hidden contours of the seafloor. Whatever the cause, the countercurrent has implications for how we understand the ocean's role in regulating climate, distributing heat and nutrients, and connecting distant regions of the sea. The water flows on in darkness, patient and persistent, following rules we are only beginning to learn.
There are places in the deep sea where bioluminescent organisms gather in such numbers that they create what can only be described as underwater constellations, fields of glowing points that twinkle and shimmer like stars seen through clear night air. These aggregations occur in the water column far from the seafloor, in the mid-water zone where darkness is absolute and the pressure immense. And the creatures that produce this light include jellyfish, squid, fish, and countless tiny invertebrates, each flashing or glowing in its own rhythm and pattern. When a submersible drifts through these gatherings, its cameras capture a spectacle of remarkable beauty, a living galaxy suspended in the deep, each light a small beacon of life in the vast emptiness. Scientists believe that many of these organisms use bioluminescence to communicate with one another, to signal readiness to mate, to coordinate movements, or to warn of danger. But the full language of light in the deep sea is far from understood. Some species produce light through chemical reactions within their own bodies, mixing luciferin and luciferase to create a glow, while others harbor symbiotic bacteria that produce light on their behalf, cultivating living lanterns in specialized organs. The reasons for such diversity, the evolutionary pressures that shaped these light-producing systems, and the roles that bioluminescence plays in deep-sea ecology are questions that continue to fascinate and challenge researchers who study them.
Certain underwater canyons serve as highways for sediment and organic matter sliding from the continental shelves into the deep ocean. But within these canyons, scientists have discovered layers of material that seem out of place. Sediments that contain shells and pollen from species that should not exist at these depths or in these time periods. These anomalies suggest that the canyons have witnessed dramatic changes in sea level or climate, events that transported coastal material far offshore, or that preserved samples of ecosystems that existed in different environmental conditions. By drilling cores into the canyon walls and analyzing the layers, researchers can read a history of the ocean written in mud and sand, a chronology of storms, currents, and climate shifts that stretches back millions of years. But some of the layers contain surprises. Pockets of freshwater diatoms in sediments deposited in deep saltwater, or chunks of wood and plant material in regions where no rivers should have reached. These findings hint at cataclysmic events, massive floods or tsunamis that carried terrestrial material far out to sea, or perhaps periods when the ocean itself was dramatically different from what we know today. The canyons cut deep and dark through the continental slopes, their walls holding stories that we are only beginning to decipher.
A few scattered locations on the seafloor emit a faint, steady glow that persists for weeks or months, a light that does not seem to come from any known bioluminescent organism, but rather from the sediment itself, as if the mud were radiating some low-level luminescence. This phenomenon has been observed by autonomous underwater vehicles equipped with sensitive cameras, instruments that patrol the ocean floor for extended periods, documenting conditions in places no human can visit. The glow is too faint to be visible to the naked eye, but clear in long exposure images, and its cause is deeply puzzling. Some researchers speculate that it might be produced by bacteria living in the sediment, microorganisms that generate light as a byproduct of metabolic processes, while others wonder if it could be a form of phosphorescence, a slow release of energy absorbed from some other source. There are also theories involving radioactive isotopes naturally present in the sediment. Isotopes that decay and release particles which then stimulate light production in certain minerals, though this explanation remains speculative. The glow continues, night after night, a quiet illumination in the deep, patient and unexplained, waiting for someone to understand its origin.
Deep below the waves, there are places where the ocean floor is marked by perfectly parallel grooves, long furrows that stretch for kilometers across the sediment, as if something massive dragged itself or was dragged across the bottom, carving lines in the mud with mechanical precision. These formations were first noticed in sonar surveys, appearing as striations too regular to be natural erosion patterns, and when cameras were sent to investigate, they revealed trenches, sometimes several meters wide and surprisingly deep, cutting through layers of accumulated sediment to expose older material beneath. The most mysterious aspect of these grooves is their uniformity. They run parallel to one another with barely any deviation, maintaining consistent spacing and depth over great distances, suggesting that whatever created them followed a deliberate path or was guided by some external force. Scientists have proposed that they might be the work of icebergs, massive chunks of glacial ice that drifted into these regions during past ice ages, their keels scraping the seafloor as currents pushed them along, leaving these scars as evidence of their passage. Others suggest that strong bottom currents might have carved the grooves, though this explanation struggles to account for the precision of the parallel patterns. The grooves remain, inscribed in the sediment, a record of forces and events we can only imagine.
Some underwater realms reveal the presence of what appear to be ancient riverbeds, channels and valleys that wind across the sea floor in patterns that resemble terrestrial drainage systems, complete with tributaries and deltas. Yet these formations lie thousands of meters below the surface, in regions that have been underwater for millions of years. The discovery of these features challenged early assumptions about the stability of sea levels and continental shelves, for they suggested that areas now deep beneath the waves were once exposed land, places where rain fell and rivers flowed and carried sediment toward ancient coastlines. These submerged valleys are particularly prominent along continental margins, where the transition from shallow coastal waters to the deep ocean reveals a landscape of drowned geography. Canyons that were carved when the ocean was lower and that now serve as conduits for turbidity currents and sediment transport. But some of these channels are found in locations and at depths that are difficult to reconcile with known sea level changes, leading researchers to wonder if other processes might be at work. Underwater avalanches carving their own paths, or tectonic movements reshaping the sea floor in ways that mimic the work of rivers. The channels wind through the darkness, empty of water that flows, filled instead with cold currents that move in silence. In regions where cold seeps release methane and other hydrocarbons from beneath the sea floor, strange mounds and structures have formed, built not by geological forces, but by the accumulated shells and skeletons of organisms that thrive in these chemically rich environments. These biological constructions can grow meters tall, reef-like formations made of mussels and tube worms and bacterial mats, all clustered around the source of methane, all dependent on the energy that chemosynthetic bacteria can harvest from the gas. The mounds create complex three-dimensional habitats in an otherwise flat landscape, and they attract a diversity of life: fish seeking shelter, crabs hunting for food, octopuses making their homes in the crevices between shells. But what makes these structures particularly intriguing is their age and their fragility. Some of them have been growing for centuries, slowly accumulating over generations of organisms, yet they are vulnerable to changes in the flow of methane, which can stop or shift without warning, as geological processes open new pathways or seal old ones. When a seep ceases, the community it supports begins to die, and the mound becomes a ghost structure, a skeletal framework gradually buried by sediment. Scientists studying these sites are racing against time, documenting these ecosystems before they vanish, trying to understand how they form, how long they persist, and what their presence tells us about the hidden chemistry of the deep.
Scientists have long wondered why certain species of deep-sea fish possess eyes that are enormous relative to their body size. Eyes that seem designed to gather every photon of light in an environment where light is scarce to the point of non-existence. These fish, with eyes like dark orbs that dominate their heads, inhabit the twilight zone of the ocean, the region where the last traces of sunlight penetrate, creating a dim, blue-gray world where vision is still possible, but barely. The adaptive value of such large eyes is clear in this zone. They allow the fish to detect the silhouettes of prey against the faint background light, or to spot the bioluminescent flashes of other organisms. But some species with these enormous eyes have been found living far below the twilight zone, in depths where no sunlight ever reaches. Why these deep-dwelling fish retain such elaborate visual apparatus when there is essentially nothing to see is a puzzle. Some researchers suggest that they may be detecting bioluminescence, that the deep sea is not as uniformly dark as we assume, that flashes and glows are common enough to make vision valuable. Others propose that these fish may migrate vertically, rising into lighter waters to feed and returning to the depths to rest, and that their eyes serve them during these excursions. The fish drift through the blackness, their eyes wide and watchful, adapted to see in a world that offers almost nothing to be seen.
Hidden far beneath the surface lies evidence of ancient volcanic activity that seems to have occurred in pulses, episodes of intense eruption, followed by long periods of quiescence, creating layered structures in the oceanic crust that tell a story of the Earth's restless interior. These layers are revealed when scientists drill into the seafloor or study exposed sections of crust in rift zones. And what they find is a complex history written in basalt and volcanic glass, a record of magma chambers filling and emptying, of tectonic plates spreading apart, and new ocean floor being born. Some of these volcanic episodes appear to have been synchronized across vast distances, as if something triggered eruptions simultaneously in multiple locations, and this has led researchers to wonder what could coordinate such events. Theories include changes in the rate of tectonic spreading or fluctuations in the mantle convection that drives plate motion, or even the influence of external factors like gravitational effects from the moon and sun, though evidence for these mechanisms remains circumstantial. The volcanic layers lie buried beneath sediment, their fires long extinguished, but they preserve clues to the dynamic processes that continue to shape our planet, clues that we are only beginning to read.
There are ocean depths where the water itself seems to stratify into layers so distinct that they barely mix, each layer maintaining its own temperature, salinity, and chemistry, creating boundaries that act almost like membranes, separating different realms within the sea. These stratifications are most pronounced in certain basins and trenches where topography restricts water circulation, trapping dense, cold, salty water at the bottom and isolating it from the layers above. Over time, the bottom water becomes oxygen depleted as organisms consume what little oxygen is present and no fresh supply arrives from the surface, creating anoxic or hypoxic zones where few animals can survive but where specialized bacteria thrive. These isolated pools can persist for years or even centuries, and when scientists take samples, they sometimes find water that is chemically unlike anything else in the ocean.
enriched in dissolved metals, high in sulfide, almost toxic by surface standards. Yet even here, life exists. Microbes that have adapted to conditions that would be lethal to most organisms. Microbes that might offer insights into how life originated on Earth, or how it might exist on other worlds with hostile environments. The layers rest one atop another, distinct and separate, a liquid stratigraphy in the darkness.
A few regions of the deep sea floor are covered in what appear to be fossilized ripples, patterns in the sediment that resemble the wave-formed ripples seen on beaches and in riverbeds. Yet these patterns are found at depths where no waves should ever reach, and where currents are too weak to shape sediment in such ways. The ripples are revealed in high-resolution images captured by autonomous underwater vehicles, and they show a regularity and symmetry that suggests they were formed by rhythmic processes, oscillating forces that moved back and forth, pushing sediment into crests and troughs. One hypothesis is that these ripples are indeed ancient, formed when the seafloor was at a different depth or when stronger currents flowed through the region, and that they have been preserved under later deposits and then re-exposed by erosion. Another possibility is that they are created by internal waves, subsurface oscillations in the density structure of the ocean that can generate currents along the seafloor, currents strong enough to move sediment even in the deep. These internal waves are invisible from the surface, but can be surprisingly powerful, and their effects on the deep-sea environment are still being studied. The ripples lie frozen in the mud, waves that never break, patterns that endure in stillness.
In the dark quiet of the ocean floor, something unusual occurs in certain areas where the sediment appears to be breathing, slowly inflating and deflating as if the seafloor itself were alive. This phenomenon, observed by time-lapse cameras left on the bottom for weeks or months, shows subtle changes in the level of the sediment surface, rises and falls of a few centimeters that happen over hours or days. The most likely explanation involves gas, methane or other hydrocarbons trapped beneath a layer of impermeable sediment, accumulating until the pressure is great enough to lift the overlying material and then escaping through cracks or pathways, allowing the sediment to settle again. This cycle can repeat, creating a rhythmic pattern of inflation and deflation, and it has significant implications for organisms living on or in the sediment, as the movement can disturb burrows, displace animals, and alter the chemical conditions they depend on. Some researchers also speculate that these breathing sediments might be related to deeper geological processes, to the slow creep of tectonic plates or the movement of fluids through faults and fractures in the crust, processes that link the seafloor to the interior of the Earth in ways that are not yet fully understood. The sediment rises and falls, inhaling and exhaling, a slow respiration in the abyss. Explorers have reported traces of what appear to be trails on the seafloor, long, meandering paths through the sediment that sometimes end abruptly or loop back on themselves, as if whatever made them paused, wandered, and then disappeared. These trails are not uncommon in the deep sea. Many bottom-dwelling animals leave tracks as they move in search of food or shelter, but some of the trails are usual in their length or their complexity, and a few seem to lead nowhere, originating in the middle of an otherwise undisturbed plain with no sign of the creature that made them. One possibility is that the tracks were made by animals that then swam up into the water column, leaving no evidence of their departure, or that they were made by organisms so delicate that they disintegrated or were consumed by scavengers before cameras could document them. Another, more speculative idea is that some trails might be old, preserved from a time when conditions were different, and that they have been covered and uncovered by shifting sediment, appearing and disappearing like ghosts. The trails wind across the seafloor, stories written in mud, beginning and ending in mystery.
Certain abyssal zones whisper of objects that rest on the ocean floor far from any shipping route or human activity. Structures that are clearly man-made, but whose presence in these remote locations is difficult to explain. Over the decades, deep-sea explorers have encountered remnants of old cables, pieces of abandoned equipment, even intact but mysterious metal frameworks. And while some of these can be traced to specific expeditions or historical events, others remain unidentified. One particularly intriguing find was a large, complex metal structure resembling a scaffold or platform, resting upright on the seafloor thousands of meters down, corroded by decades or centuries of seawater, but still intact. No records exist of any operation that would have placed such an object in that location, and its design does not match any known equipment from the era in which it appears to have been constructed. Theories range from secret military operations to failed early attempts at deep-sea mining, but without documentation, the truth is lost to history. The ocean has become an archive of human activity, some of it deliberate, some accidental, and much of it forgotten. And these relics rest in darkness, monuments to endeavors whose purposes are no longer known.
Deep below the waves, there are places where the concentration of a particular element or compound is far higher than it should be, creating chemical anomalies that puzzle oceanographers and geochemists. One such anomaly involves helium-3, a rare isotope of helium that is found in much higher concentrations in certain parts of the deep ocean than can be explained by atmospheric sources or the decay of terrestrial materials. The excess helium-3 is believed to come from the Earth's mantle, released at hydrothermal vents and mid-ocean ridges where tectonic plates pull apart and magma rises from below. This discovery has important implications for understanding the planet's interior, as the ratio of helium isotopes provides clues about the composition and dynamics of the mantle. But it also raises questions about how these materials are transported and distributed through the ocean. Some regions show much higher helium-3 concentrations than others, suggesting that there are plumes or currents that carry the gas far from its source, and tracing these paths helps scientists map the hidden circulation of the deep sea. The helium rises, invisible and inert, a breath from the Earth's core dispersing into the cold water.
In the endless black of the abyss, there exists a type of sediment known as red clay, a fine-grained material that accumulates incredibly slowly, at rates measured in millimeters per 1,000 years, covering the deepest and most remote parts of the ocean floor. Unlike other deep-sea sediments, which are largely composed of the shells and skeletons of plankton, red clay forms from the weathering of volcanic material and the gradual settling of dust from the atmosphere, particles that drifted across the globe before falling into the sea. The red color comes from iron oxides, rust in its essence, and the clay is among the oldest continuously accumulating materials on Earth, preserving a record of atmospheric conditions, volcanic eruptions, and even cosmic events like asteroid impacts. Embedded in the red clay, scientists have found tiny spherules of extraterrestrial origin, micrometeorites that survived their passage through the atmosphere and now rest on the seafloor, evidence of the constant, gentle rain of material from space. The clay accumulates grain by grain, patient and persistent, building a history so slow that it is almost beyond comprehension.
Some deep-sea regions hold fossils of organisms that are millions of years old, species that lived in warm, shallow seas that once covered areas now submerged in the cold abyss. And the presence of these fossils in such locations tells of dramatic changes in the Earth's surface, of continents drifting, ocean basins opening and closing, and sea levels rising and falling. These fossils are not merely scientific curiosities. They are evidence of the planet's dynamism,
proof that what we see today is just one frame in a very long film. Among the most striking finds are fossils of tropical corals and mollusks in regions now far too deep and cold for such organisms to survive, suggesting that these areas were once close to the surface, perhaps even exposed to sunlight, before tectonic subsidence or sea level rise moved them into the depths. Other fossils are of species that are completely extinct, lineages that thrived for millions of years and then vanished, leaving only their shells and bones as testament to their existence. The fossils rest in the sediment, fragments of ancient life, windows into worlds that no longer exist. Far below, in the crushing pressure, something mysterious unfolds in the deepest trenches. The Hadal zones, named after Hades, the ancient Greek underworld, where the seafloor plunges more than 6,000 meters below the surface, and conditions become truly extreme. These trenches form at subduction zones, places where one tectonic plate slides beneath another, dragging the seafloor down into the mantle and creating some of the most geologically active and least explored places on Earth. Life in the trenches is sparse, but surprisingly diverse, with species that are found nowhere else. Organisms that have evolved in isolation for millions of years, adapting to pressures that exceed 1,000 atmospheres, temperatures just above freezing, and total darkness. Among the creatures discovered here are amphipods, shrimp-like crustaceans that can grow to remarkable sizes, and snailfish, delicate-looking but incredibly resilient fish that represent the deepest living vertebrates known. But the trenches hold more than just unusual life. They also trap sediment and organic matter that slides down from the surrounding slopes, accumulating in the deepest points and creating pockets of high biological activity despite the harsh conditions. What happens in these pockets, how nutrients cycle through them, and what role they play in the larger ocean system are questions that researchers are only beginning to address.
Long ago, researchers detected hints of deep-sea currents that seemed to pulsate, flowing strongly for a period and then weakening or even reversing direction, oscillating in cycles that might be linked to tides, to seasonal changes in surface conditions, or to forces entirely internal to the ocean itself. These pulsations were discovered through long-term monitoring with moored instruments, current meters that record flow speed and direction continuously over months or years, and the data revealed patterns that were unexpected and complex. In some cases, the pulsations appeared to be driven by internal tides, oscillations generated by the interaction of tidal forces with underwater topography, which create waves that propagate through the ocean interior and generate currents that wax and wane with predictable rhythms. In other cases, the pulsations seemed less regular, more chaotic, perhaps influenced by eddies and turbulence generated by the interaction of different water masses. Understanding these currents is important for modeling the ocean's circulation and its role in climate, for these deep flows transport heat, salt, and nutrients over vast distances, connecting equatorial and polar regions, surface and abyss. The currents pulse and flow, invisible rivers in the darkness, never still, always changing.
There are places in the deep sea where the diversity of life spikes unexpectedly, small areas that support far more species than the surrounding regions, creating what ecologists call biodiversity hotspots, though the reasons for these concentrations are not always clear. Some hotspots are associated with features like seamounts or cold seeps, places where food is more abundant or where hard substrate allows sessile organisms to settle. But other hotspots occur in seemingly ordinary stretches of seafloor, flat plains with no obvious special characteristics. One hypothesis is that these areas serve as refugia, places where conditions have remained stable for long periods, allowing species to accumulate over time without the disruptions of environmental change.
Another idea is that they are located at the intersection of different water masses or currents, zones where nutrients and larvae from multiple sources converge, creating opportunities for colonization and speciation. Studying these hotspots helps scientists understand the factors that promote biodiversity and the processes that shape ecological communities. But it also highlights how much we still have to learn about the spatial patterns of life in the deep sea. The hotspots glow, metaphorically, with life, bright patches in a dark, sparse landscape.
Drifting in the silent blue, one may encounter the remains of ancient landslides, massive collapses of the continental slope that sent billions of tons of rock and sediment tumbling into the abyss, events so catastrophic that they would have generated tsunamis and reshaped the seafloor over areas the size of entire countries. Evidence of these landslides is preserved in the geological record, in the chaotic deposits they left behind, and in the scars they carved into the slope, scars that are visible in sonar images as amphitheater-shaped hollows, the source regions where the material broke away and began its descent. Some of these landslides occurred thousands or millions of years ago, but others are geologically recent, and there is concern that future events could be triggered by earthquakes, volcanic eruptions, or even human activities like drilling and mining. The tsunamis generated by underwater landslides can be devastating to coastal communities, and understanding where and when such events might occur is an important goal for geologists and hazard planners. The remnants of old landslides lie scattered across the deep seafloor, testament to the power of gravity and the instability of the ocean margins.
In regions where underwater volcanic activity builds new islands or adds material to existing ones, mysterious vents sometimes appear offshore, releasing fluids that are neither hot like hydrothermal vents nor cold like typical seeps, but somewhere in between, warm enough to create shimmering distortions in the water, but not hot enough to cook the organisms that gather around them. These lukewarm vents are puzzling because their temperature suggests a mixing of sources, perhaps water that has circulated through volcanic rock but cooled before emerging, or a combination of groundwater and seawater heated by residual geothermal energy. The chemistry of these vents is also unusual, often enriched in dissolved gases and nutrients, but lacking the extreme concentrations of metals and sulfides found at hotter systems. The organisms that colonize lukewarm vents are different too, often including species more typical of shallow coastal environments rather than the specialized vent fauna, as if these systems represent a transitional habitat, a middle ground between the volcanic deep and the sunlit shallows. Scientists studying these vents are interested in how they form, how long they persist, and what role they might play in connecting different marine ecosystems. The warm water rises in lazy spirals, not violent plumes, and the life around them seems almost leisurely in comparison to the frenzy of hotter vents.
Scientists have long wondered why certain deep-sea organisms exhibit bioluminescence in colors other than the typical blue-green, producing flashes of red or even yellow light that are rare and energetically expensive to generate, yet must serve some important function to have evolved. Blue-green light is most common in the deep sea because water absorbs other wavelengths more strongly, meaning blue-green light travels farther and is more effective for communication or predation. But red light is absorbed so quickly that it can only be seen at very close range. Some fish and crustaceans have evolved to produce red bioluminescence, and they also possess visual systems sensitive to red light, creating a private communication channel invisible to most other deep-sea creatures. This red light might be used to illuminate prey without alerting them, since most deep-sea animals cannot see red. Or it might serve as a covert signal between members of the same species, a way to find mates or coordinate behavior without broadcasting to potential predators. The evolutionary innovations required to produce and detect red light suggest that the advantages must be significant, yet the details of how these systems are used in the wild remain largely observational, glimpsed briefly during submersible dives, but not yet fully understood.
The red lights flash in the darkness like distant embers, visible only to those with eyes to see them.
Certain underwater canyons serve as conduits for dense water masses that cascade down the continental slope like underwater waterfalls, flows of cold, salty water that sink because they are denser than the surrounding ocean, creating currents that can persist for days or weeks and that transport enormous volumes of water and sediment into the abyss. These cascades are triggered by specific conditions, often during winter when coastal waters cool and become denser, or when evaporation in shallow areas increases salinity. And when they occur, they can dramatically affect the environment through which they flow. The dense water hugs the bottom as it descends, carrying oxygen from the surface into the deep and stirring up sediment as it passes. And organisms living in the canyons must cope with these periodic disturbances, either by retreating to sheltered areas or by adapting to tolerate the sudden changes in temperature, salinity, and turbidity. The cascades also play an important role in the ocean's circulation, helping to drive the thermohaline circulation that connects surface and deep waters around the globe. The water pours down through the canyons, silent and relentless, an invisible torrent in the darkness.
A few underwater realms reveal the presence of what appear to be petrified forests, stands of ancient trees that sank to the sea floor thousands or millions of years ago, and that have been preserved in the cold, dark, oxygen-poor conditions of the deep. These submerged forests are rare, but when they are found, they offer remarkable opportunities to study wood-boring organisms and the processes of organic decay in extreme environments. The trees, waterlogged and heavy, rest on the bottom with their branches reaching up into the water column, and over time they become colonized by bacteria, fungi, and specialized animals like shipworms, which are actually mollusks that have evolved to bore into wood and digest cellulose with the help of symbiotic microbes. The presence of wood in the deep sea creates a temporary food source, a concentration of organic carbon in an otherwise carbon-poor environment, and it supports communities that are distinct from those found on surrounding sediment or rock. Some of the trees have been dated and found to be ancient, having fallen into rivers during storms or landslides and then carried out to sea, where they drifted until they became waterlogged and sank. The forests lie in darkness, silent and still, their leaves long gone, their roots no longer connected to soil, yet still providing life and shelter in their slow decay.
Hidden far beneath the surface lies evidence of catastrophic events that reshaped the ocean basin. Sudden shifts in the seafloor that created scarps and cliffs hundreds of meters high. Boundaries between areas at different depths that mark where the crust broke and moved. These features are the result of tectonic activity, of earthquakes and faulting that occur along the boundaries of the great plates that make up the Earth's surface. And they are reminders that the ocean floor is not a static, unchanging place, but a dynamic landscape, constantly being created, destroyed, and rearranged. Some of these scarps are very old, weathered and softened by millions of years of sediment accumulation, while others are geologically young, sharp and fresh, with exposed rock faces where sediment has not yet had time to accumulate. Organisms living near these scarps often take advantage of the vertical structure, attaching to the rock walls where they are elevated above the sediment and have access to currents that bring food and oxygen. The scarps rise from the seafloor like walls, dividing different realms, boundaries between depths and habitats, monuments to the forces that shape the planet.
In the dark quiet of the ocean floor,
Something unusual occurs when currents flowing over complex topography create vortices and eddies that spin off and propagate through the water column, carrying trapped water masses with them as they move. These deep-sea eddies can be enormous, hundreds of kilometers across, and they can persist for months or even years, slowly drifting through the ocean while maintaining their structure and identity. Inside an eddy, the water has its own temperature and salinity characteristics, different from the surrounding ocean, and it carries with it nutrients, larvae, and even adult organisms, transporting them far from their original locations. Eddies can cross entire ocean basins, connecting distant ecosystems and distributing species in ways that would otherwise be impossible, and they play a crucial role in the mixing and circulation of the deep sea. Tracking these eddies is challenging because they are invisible from the surface and move slowly through the depths, but satellite observations of sea surface height and temperature combined with data from drifting floats have allowed scientists to map their paths and study their effects. The eddies spin through the darkness, self-contained worlds within the ocean, carrying their secrets with them.
Some deep-sea regions hold concentrations of glass sponges, delicate organisms with skeletons made of silica that form intricate lattice-like structures resembling spun glass or fine lacework. These sponges can grow to impressive sizes, reaching several meters in height, and they often occur in dense aggregations called sponge gardens or sponge reefs, which provide habitat for a diverse array of other organisms. The glass sponges filter water through their bodies, extracting bacteria and organic particles for food, and they grow very slowly, with some individuals estimated to be hundreds or even thousands of years old. What makes these sponge concentrations mysterious is their patchy distribution. They occur in some areas but are absent from seemingly similar habitats nearby, and the factors that determine where they can establish and thrive are not entirely clear. Water flow appears to be important as sponges need currents to deliver food and remove waste, but other factors like substrate type, temperature, and the presence of predators or competitors also play roles. Some of the largest sponge reefs are found off the coast of British Columbia, where they were only discovered in the late 20th century and have since been recognized as ecosystems of significant ecological importance worthy of protection from human disturbance. The sponges stand like crystal cathedrals in the darkness, fragile and ancient, filtering the water with patient persistence.
Explorers have reported traces of unusual acoustic phenomena in certain parts of the ocean, sounds that are detected by underwater listening devices, but that do not match any known biological or geological source, and that sometimes occur in patterns suggesting regularity or repetition. Among the most famous of these is the bloop, a powerful ultra-low frequency sound recorded in 1997 by hydrophones in the Pacific Ocean, which was initially mysterious but later attributed to ice quakes, the sounds of icebergs fracturing and breaking apart. Other sounds remain less well explained, including various whistles, moans, and pulses that appear sporadically in the ocean's acoustic record. Some of these may be produced by unknown species of whales or other marine mammals using vocalizations we have not yet documented, while others might originate from geological processes like underwater landslides, volcanic activity, or the movement of fluids through fissures in the crust. The ocean is filled with sound, a cacophony of biological, geological, and anthropogenic noises, and distinguishing the sources and understanding their significance is an ongoing challenge for researchers. The sounds propagate through the water, traveling for hundreds or thousands of kilometers, and somewhere in the darkness they find receivers, ears, sensors, membranes that perceive them, even if we do not yet understand their meaning.
Deep below the waves, there are places where the seafloor is covered in a layer of shells so thick and extensive that it resembles a desert of calcium carbonate.
a white plain stretching to the horizon in all directions. These shell deposits are the accumulated remains of pteropods, tiny planktonic snails with delicate transparent shells, which live in the surface waters and rain down to the bottom when they die. Pteropods are incredibly abundant in some parts of the ocean, and their shells can dominate the sediment in certain regions, creating what are known as pteropod oozes. However, these shells are made of a form of calcium carbonate that is particularly vulnerable to dissolution in cold, deep, acidic water. And as the ocean absorbs more carbon dioxide from the atmosphere and becomes more acidic, the depth at which pteropod shells dissolve is rising, threatening to erase these deposits and disrupt the ecosystems that depend on them. The loss of pteropod shells from the deep sea would have cascading effects, altering the chemistry of the sediment, affecting the organisms that live there, and changing the ocean's ability to store carbon. The shell deserts lie in the darkness, monuments to abundance and vulnerability, accumulations that speak of life in the sunlit layers above and of the delicate balance that governs the deep.
Far below, in the crushing pressure, something mysterious unfolds in the bodies of certain deep-sea organisms that produce antifreeze proteins, molecules that prevent ice crystals from forming in their tissues despite living in water that is cold enough to freeze. These proteins are found in fish that inhabit polar and deep-sea environments, and they work by binding to tiny ice crystals and preventing them from growing larger, allowing the organisms to remain active and supple even in frigid conditions. The evolution of antifreeze proteins is a remarkable example of adaptation to extreme environments, and studying these molecules has provided insights into the biochemistry of cold tolerance and has even inspired applications in biotechnology, including the preservation of organs for transplant and the development of cold-resistant crops. But the mystery extends beyond the proteins themselves to questions about how such complex adaptations arose, how they are regulated, and what other strategies deep-sea organisms use to cope with cold. The fish drift through icy water, their blood protected by molecular guardians, their survival a testament to the inventiveness of evolution.
Certain abyssal zones whisper of magnetic bacteria, microorganisms that contain chains of magnetite crystals, which they use to orient themselves along the Earth's magnetic field, navigating through the water column or sediment with a biological compass. These magnetotactic bacteria were first discovered in shallow environments, but have since been found in deep-sea sediments, where they play a role in the cycling of iron and other elements. The magnetite crystals, called magnetosomes, are formed within specialized compartments inside the bacterial cells, and they are remarkably uniform in size and shape, suggesting precise biological control over their synthesis. Scientists are interested in magnetotactic bacteria not only for their unusual biology, but also for what they can tell us about the ancient Earth, as fossil magnetosomes have been found in rocks dating back billions of years, potentially providing evidence of some of the earliest life on the planet. The bacteria align and swim, following invisible lines of force, guided by the planet's magnetic field through the darkness.
There are ocean depths where the remains of shipwrecks rest, vessels that sank decades or centuries ago and that now serve as artificial reefs, colonized by deep-sea organisms and slowly being consumed by bacteria, worms, and other decomposers. These wrecks are time capsules, preserving artifacts and cargo from the era in which they sank. But they are also dynamic ecosystems, changing as metal corrodes, wood decays, and organisms settle and grow. Some wrecks are well known and have been extensively studied or even salvaged, while others remain undiscovered, their locations lost to history, lying in darkness, visited only by the occasional curious fish or passing current.
The deep sea is a graveyard for ships, a repository of maritime history scattered across the ocean floor, and each wreck tells the story of human ambition, tragedy, and the enduring power of the sea. The hulls rest on the bottom, their holds filled with sediment instead of cargo, their decks encrusted with corals and sponges, monuments to journeys ended and lives lost.
In the endless black of the abyss, there exists a phenomenon where bioluminescent organisms create what researchers call burglar alarms, defensive displays of light intended not to attract mates or lure prey, but to draw the attention of larger predators to whatever is attacking them. This strategy is used by certain jellyfish and other planktonic creatures, which, when seized by a predator, flash brightly in a pattern designed to be conspicuous, essentially calling for help by advertising the predator's location to its own predators. The logic is elegant. If a small jellyfish is caught by a fish, its flashing might attract a larger fish that will eat the predator, allowing the jellyfish to escape in the confusion, or at least ensuring that the predator thinks twice before attacking such conspicuous prey again. Evidence for this behavior comes from observations of bioluminescent displays triggered by mechanical stimulation, mimicking the sensation of being grabbed, and from the fact that many deep-sea predators are highly sensitive to light and will investigate flashes in the hope of finding food. The burglar alarm hypothesis illustrates the complex interplay of strategies and counter-strategies that have evolved in the deep sea, where every flash of light is a signal, every signal a potential advantage or risk. The lights flash in alarm, beacons of distress, calling through the darkness for salvation or revenge.
Long ago, researchers detected hints of deep-sea bacteria that can survive on surprisingly little energy, metabolizing so slowly that they divide only once every century or even longer, existing in a state of near-suspended animation, yet still technically alive. These oligotrophic bacteria live in deep sediments and other low-energy environments where organic matter is scarce and conditions are stable, and they represent an extreme end of the spectrum of life strategies. Their slow metabolism allows them to persist for millennia, waiting patiently for conditions to improve, for a sudden influx of nutrients that might allow them to become more active. And studying them challenges our assumptions about what life requires and how it can be sustained. Some scientists have speculated that such organisms might be analogs for life on other planets or moons, places where energy is limited but where stable conditions could allow slow, patient life to endure. The bacteria rest in the sediment, almost but not quite inert. Their existence measured not in days or years, but in centuries, a different kind of life unfolding on a different timescale. Drifting in the silent blue, one may encounter the larvae of deep-sea organisms, tiny, transparent creatures, barely visible even under magnification, drifting in the water column far from the seafloor, where they will eventually settle and mature. These larvae are often very different in appearance from their adult forms, with delicate bodies adapted for drifting rather than crawling or swimming, and they can spend weeks or months in the plankton before finding suitable habitat and undergoing metamorphosis. The larval stage is crucial for dispersal, allowing species to colonize new areas and maintain genetic connections between distant populations. But it is also a time of high mortality, as the larvae are vulnerable to predation, starvation, and being carried into unsuitable environments by currents. Scientists studying deep-sea larvae are interested in understanding how they navigate, how they sense the sea floor and decide where to settle, and what factors determine their survival and success. The larvae drift through the darkness, microscopic seeds of life, carried by currents beyond their control,
searching for the right place to begin their adult existence.
A few scattered locations on the seafloor emit faint traces of radioactivity, natural radiation from isotopes present in the sediment or released from the crust, creating hotspots of elevated radioactivity that are usually harmless but occasionally high enough to be of scientific interest. These radioactive zones can result from the concentration of certain minerals, like uranium-bearing ores that have accumulated through geological processes, or from the decay of organic matter that has absorbed radioactive elements from the water. In some cases, human activity has contributed to the radioactivity, as nuclear tests, accidents, and waste disposal have left traces of artificial isotopes in the ocean, though these tend to be diluted and dispersed by currents over time. Measuring radioactivity in the deep sea helps scientists understand geochemical cycles, trace the movement of water masses, and assess the long-term impacts of human activities on marine environments. The radiation glows invisibly, its presence known only through instruments, its energy slowly dissipating into the surrounding water and sediment. Some underwater realms reveal the presence of ancient coral reefs, now buried under layers of sediment, but preserved in sufficient detail that their structure and composition can be studied through drilling and core sampling. These fossil reefs tell stories of past climates, of times when the ocean was warmer or colder, when sea levels were higher or lower, and when the chemistry of seawater was different from what it is today. By analyzing the skeletons of the corals and the organisms that lived alongside them, scientists can reconstruct environmental conditions from millions of years ago, creating a history of the Earth's climate system that extends far beyond the instrumental record. Some of these ancient reefs are found in locations that are now too deep or too cold for reef-building corals, evidence of how the planet has changed and how the distribution of life has shifted in response. The reefs lie buried, their structures intact, silent archives of ancient seas.
In regions where fresh water seeps into the ocean from underground aquifers, strange interfaces form between the fresh and salt water, zones where the two fluids mix only slowly, creating layers with distinct properties and supporting unique communities of organisms adapted to brackish conditions. These submarine springs are found in various locations around the world, often near coastlines or on the continental shelf, and they can discharge significant volumes of water, sometimes forming visible plumes that rise through the denser seawater like underwater fountains. The mixing zone between fresh and salt water is chemically dynamic, with gradients in salinity, dissolved oxygen, and nutrients that create microhabitats for specialized bacteria and other microorganisms. Some submarine springs also release dissolved minerals and gases from deep underground, adding to the chemical complexity of these environments. Studying these springs helps scientists understand groundwater systems, coastal geology, and the connections between terrestrial and marine ecosystems. And it also raises questions about how much fresh water is being discharged into the ocean from sources we have not yet identified or measured. The fresh water rises through the salt, lighter and different, creating boundaries and mixing zones in the darkness.
Scientists have long wondered why certain deep-sea species exhibit extraordinary longevity, living for decades or even centuries in environments where food is scarce, temperatures are low, and metabolic rates are reduced to conserve energy. Among the longest-lived organisms in the ocean are certain species of cold-water corals, sponges, and fish, which grow extremely slowly and can reach ages that rival or exceed the oldest terrestrial organisms.
One species of Greenland shark, for example, has been found to live for over 400 years, making it the longest-lived vertebrate known to science, and its slow growth and late maturity are adaptations to the cold, stable conditions of the deep Arctic and North Atlantic waters where it dwells. The mechanisms underlying such extreme longevity are of great interest to biologists studying aging, as understanding how these organisms avoid the cellular damage and dysfunction that typically accompany aging in other species could provide insights into the fundamental processes of senescence and mortality. The creatures drift through the centuries, patient and enduring, witnesses to changes in the ocean and the world above that unfold on timescales few other organisms experience.
Certain underwater canyons serve as natural laboratories for studying turbidity currents, the underwater avalanches of sediment-laden water that flow down the canyon channels and onto the abyssal plains beyond. And scientists have deployed instruments in these canyons to measure the speed, thickness, and composition of these currents when they occur. The data collected has revealed that turbidity currents can travel at surprising speeds, sometimes exceeding tens of kilometers per hour, and that they can carry enormous quantities of material, reshaping the canyon floor and depositing sediment in distinctive patterns that can be recognized in the geological record. These currents are triggered by various events, earthquakes, storms, or simply the accumulation of unstable sediment on steep slopes, and predicting when and where they will occur is difficult, making direct observation rare and valuable. The canyons channel the currents, focusing their energy and directing their flow, and the scars they leave behind are visible in sonar images as sinuous pathways carved through the continental slope, testament to the power of moving sediment.
Hidden far beneath the surface lies evidence of ancient hydrothermal vent fields that are no longer active, their chimneys cold and silent, their communities of specialized organisms extinct or dispersed, leaving only the mineral deposits they created as markers of their former existence. These inactive vents are found on old sea floor far from current tectonic activity, and they provide a window into the history of ocean chemistry, volcanic processes, and biological evolution. The mineral deposits, composed of sulfides and oxides of iron, copper, zinc, and other metals, are of interest not only for their scientific value, but also for their potential economic value, as some are rich enough in metals to be considered potential targets for deep-sea mining. However, the environmental impacts of mining these deposits are poorly understood, and there is concern that extracting them could damage ecosystems that depend on the minerals as substrate or that are adapted to the unique chemical conditions they create. The inactive vents stand like monuments in the darkness, relics of fire and life now extinguished, their minerals slowly dissolving back into the seawater.
In the dark quiet of the ocean floor, something unusual occurs when dense aggregations of deep-sea urchins gather in certain areas, sometimes carpeting the seafloor in such numbers that little sediment is visible between their spiny bodies, creating what researchers call urchin barrens or urchin fronts. These aggregations can have significant ecological impacts, as urchins are voracious grazers that consume algae, detritus, and other organic matter, and when they occur in high densities, they can strip an area of food and alter the structure of the benthic community. The reasons for these aggregations are not always clear. They may be driven by the availability of food, by reproductive behavior, or by environmental conditions that favor urchin survival, but the result is a dramatic change in the local ecosystem.
In some regions, urchin populations have exploded following the removal of predators like sea otters or large fish, leading to concerns about trophic cascades and the importance of maintaining balanced predator-prey relationships. The urchins move slowly across the seafloor, their tube feet and spines propelling them in search of food, their populations waxing and waning in response to forces both biological and physical.
Some deep-sea regions hold deposits of phosphorite, sedimentary rocks rich in phosphorus that form under specific conditions related to ocean chemistry and biological productivity. Phosphorites are valuable as sources of fertilizer, and there has been interest in mining them from the sea floor, but their formation is not entirely understood, and their presence in certain locations is puzzling. Phosphorus is an essential nutrient for all life, and its availability often limits biological productivity in the ocean, so the concentration of phosphorus into rock deposits represents a significant loss from the active nutrient cycle. Understanding how and why phosphorites form helps scientists reconstruct past ocean conditions, particularly periods of high biological productivity or unusual circulation patterns, and it raises questions about the long-term cycling of nutrients and the factors that control the ocean's fertility. The phosphorite deposits rest on the sea floor, inert and patient, accumulations of an element crucial to life, locked away in stone. Explorers have reported traces of deep-sea trenches where the walls are not smooth slopes, but instead are stepped, with terraces and ledges that suggest periods of stability punctuated by sudden collapses or shifts. These stepped profiles are the result of complex interactions between tectonic forces, erosion, and sediment accumulation, and they create a variety of microhabitats at different depths and angles, each with its own conditions of light, or lack thereof, current and sediment type. Organisms living on these walls must adapt to vertical surfaces, often attaching firmly to the rock to avoid being swept away by currents, and the diversity of life on trench walls can be surprisingly high, with species that are rarely found elsewhere. The stepped topography also affects how sediment moves through the trench, creating pockets where material accumulates and other areas where it is scoured away, leading to a patchy distribution of resources and organisms. The walls descend in stages, each terrace a different world, each step a boundary between zones.
Deep below the waves, there are places where the seafloor is marked by circular depressions that appear to be the result of expelled fluids. Places where pressurized water or gas has burst through the sediment and created craters or pockmarks, some of them dozens of meters across and several meters deep. These features are common in areas where methane or other hydrocarbons are present in the subsurface, and they form when the pressure of the trapped fluids exceeds the strength of the overlying sediment, causing sudden eruptions that expel material and create the depression. Pockmarks can be active, with ongoing fluid seepage and associated biological communities, or they can be inactive, relic features that mark the sites of ancient eruptions. Understanding pockmarks is important for several reasons, including their potential role in releasing greenhouse gases into the ocean and atmosphere, their impacts on seafloor stability, and their significance as indicators of subsurface hydrocarbon deposits. The pockmarks dot the seafloor like scars, evidence of forces beneath, reminders that the ocean bottom is not solid and inert, but dynamic and full of hidden pressures.
A few underwater realms reveal the presence of deep-sea cephalopods, including octopuses and squid that have adapted to life in the abyss with modifications that seem almost alien, such as gelatinous bodies that reduce the energy cost of maintaining buoyancy, bioluminescent organs for communication or predation, and sensory systems tuned to detect the faintest traces of movement or chemical signals. Among the most mysterious of these are the deep-sea octopuses that brood their eggs for months or even years, sitting motionless on the seafloor, guarding their clutches without feeding. A reproductive strategy that requires extraordinary endurance and that raises questions about how they sustain themselves during this period. One species, observed brooding in the Monterey Canyon, was monitored over a period of 4.5 years, the longest egg brooding period ever recorded for any animal. And when the eggs finally hatched, the female was emaciated, having sacrificed herself to ensure the survival of her offspring. The cephalopods drift and crawl through the darkness, intelligent and adaptable, masters of camouflage and escape, yet also vulnerable, their lives brief and intense, their strategies for survival as varied as the environments they inhabit.
Certain abyssal zones whisper of deep-sea brine pools, pockets of extremely salty water that accumulate in depressions on the sea floor, and that are so dense they do not mix with the overlying seawater, but instead form distinct, stable layers that can persist for centuries. These brine pools are often associated with the dissolution of ancient salt deposits buried beneath the seafloor, and they create extreme environments where salinity can be several times higher than normal seawater, creating conditions that are toxic to most marine life, but that support specialized bacteria and archaea adapted to high salt concentrations. The boundaries of brine pools are often marked by dense mats of mussels or other organisms that thrive on the methane and sulfides released along with the brine. And the pools themselves can contain strange formations, including underwater rivers of brine that flow along the seafloor, following the topography like liquid mercury. Submersibles diving into these regions can actually land on the surface of a brine pool, floating on the denser fluid as if it were solid ground, a surreal experience that highlights the physical strangeness of these environments. The brine pools rest in their depressions, toxic and still, islands of inhospitable chemistry in an already extreme world. Far below, in the crushing pressure, something mysterious unfolds in the genetics of deep-sea organisms, which often show evidence of horizontal gene transfer, the exchange of genetic material between unrelated species through mechanisms other than reproduction, a process more commonly associated with bacteria, but apparently also occurring in some deep-sea animals. This phenomenon has been documented in certain worms and other invertebrates that possess genes clearly derived from bacteria, genes that code for enzymes useful for digesting unusual compounds or for tolerating extreme conditions. The presence of these foreign genes suggests that deep-sea organisms have incorporated genetic material from their environment or from their symbiotic partners, blurring the lines between species and creating hybrid genomes that challenge traditional concepts of evolution and heredity. Understanding how horizontal gene transfer occurs in multicellular organisms, how frequently it happens, and what advantages it confers are active areas of research, with implications for our understanding of evolution, symbiosis, and the adaptability of life. The genes pass between organisms, carried by viruses or other vectors, silently altering genomes in ways that can be detected only by careful sequencing and analysis.
There are ocean depths where the sediment contains layers of volcanic ash, evidence of massive eruptions that occurred on land or underwater, and that spread ash over vast areas of the ocean, creating time markers in the geological record that can be used to correlate events across different locations. These ash layers, called tephra, are particularly useful for dating and understanding the timing of geological and climatic events, as they represent instantaneous deposits from single eruptions and can be identified by their unique chemical compositions. Some ash layers in deep-sea sediments have been traced back to specific volcanoes and eruptions, including supereruptions that ejected hundreds or thousands of cubic kilometers of material and had global impacts on climate and ecosystems. The ash settles slowly through the water column, eventually blanketing the seafloor in a thin layer that, over time, becomes compacted and preserved within the sediment, a snapshot of a moment of catastrophic violence frozen in the geological record. The ash lies in layers, gray and fine, evidence of explosions that darkened skies and altered the course of history.
In the endless black of the abyss, there exists a curious behavior observed in some deep-sea fish, which appear to use bioluminescence not for communication or predation, but for camouflage, producing light on their undersides that matches the faint downwelling light from above, effectively erasing their silhouettes and making them invisible to predators looking up from below. This strategy, called counter-illumination, requires precise control of light intensity and color, as the ambient light in the deep sea changes with depth, time of day, and water clarity, and the fish must adjust their bioluminescence to match these variations. The organs that produce this ventral light, called photophores, are arranged in patterns along the belly and flanks of the fish, and they're often controlled by hormones or nerves that modulate their output in response to sensory input from the eyes or other receptors. Counter-illumination is an elegant solution to the problem of being visible in the twilight zone, where there is just enough light to create shadows but not enough to see clearly. And it illustrates the sophisticated adaptations that have evolved in response to the unique challenges of deep-sea life. The fish glow faintly from below, their light perfectly tuned, their shadows erased, invisible to those who would hunt them.
Long ago, researchers detected hints of deep-sea earthquakes, seismic events that occur along faults and fractures in the oceanic crust, often at mid-ocean ridges or subduction zones, and that release energy in ways that can be detected by seismometers around the world. These earthquakes are part of the dynamic processes that shape the ocean floor, and they provide valuable information about tectonic activity, plate boundaries, and the structure of the Earth's interior. Some deep-sea earthquakes are followed by tsunamis, as the sudden movement of the seafloor displaces water and creates waves that propagate outward at high speeds. And understanding these events is crucial for hazard assessment and early warning systems. Other earthquakes trigger underwater landslides or turbidity currents, setting off cascades of secondary events that further reshape the seafloor. The ocean bottom trembles and shifts, releasing stresses that have accumulated over years or decades, and the waves generated by these movements travel through the water and the rock, carrying information about the hidden forces that drive the planet's geology.
Drifting in the silent blue, one man countered the mysterious phenomenon of marine snow, a continuous rain of organic particles falling from the surface waters toward the seafloor, carrying with it the remains of plankton, fecal pellets, mucus strands, and other detritus, all slowly descending through the water column like an underwater blizzard. Marine snow is the primary source of food for many deep-sea organisms, and its abundance and composition vary with the seasons, with plankton blooms in the surface waters producing pulses of material that reach the deep sea weeks or months later. The particles aggregate as they fall, sticking together to form larger flakes that sink faster, and they're colonized by bacteria that break them down and recycle nutrients, making the descent of marine snow an active ecological process rather than a passive settling. Studying marine snow helps scientists understand the biological pump, the process by which carbon is transported from the atmosphere and surface ocean into the deep sea, where it can be stored for hundreds or thousands of years, and it highlights the connections between surface and deep ecosystems. The snow falls endlessly, a silent drift of sustenance, connecting the light and the dark.
Some deep-sea regions hold evidence of ancient meteor impacts, craters and ejecta layers that mark where asteroids or comets struck the ocean millions of years ago, creating explosions that would have generated tsunamis, ejected material into the atmosphere, and potentially caused mass extinctions. These impact sites are rare and often difficult to identify, as they have been buried under sediment or altered by tectonic processes. But when they are found, they provide dramatic evidence of the violent history of our planet and the role that extraterrestrial events have played in shaping life on Earth. One of the most famous impact sites is the Chicxulub crater, located partly under the Yucatan Peninsula and partly under the Gulf of Mexico, which is associated with the mass extinction that ended the age of the dinosaurs 66 million years ago. The energy released by such impacts is almost unimaginable, equivalent to billions of nuclear weapons, and the effects on the environment would have been catastrophic, with global fires, darkened skies, and climate disruptions lasting for years. The craters rest beneath the sediment, scars from space, reminders of the fragility of life and the power of cosmic forces.
Certain underwater canyons serve as routes for the migration of certain deep-sea species, which travel along these corridors in response to seasonal changes, reproductive cycles, or the availability of food. And tracking these migrations helps scientists understand the movement patterns and life histories of organisms that are otherwise difficult to study. Some migrations are vertical, with animals moving up and down the water column each day or night, while others are horizontal, with species traveling along the seafloor or through the mid-water zone over distances of hundreds or thousands of kilometers. The reasons for migration can vary. Some organisms follow the movements of their prey. Some seek specific environmental conditions for spawning. And some may simply be responding to chemical or physical cues that guide them toward favorable habitats. Understanding these migrations is important for conservation, as it reveals the connectivity between different regions of the ocean and the potential impacts of human activities like fishing, mining, or shipping on migratory species. The creatures move through the darkness, following ancient routes, guided by instincts honed over millions of years.
In regions where deep-sea corals grow, their skeletal structures serve as archives of ocean conditions, recording information about temperature, salinity, and chemistry in the layers they add year by year, much like tree rings record conditions on land. Scientists can extract cores from these coral skeletons and analyze the chemical composition of each layer, reconstructing a history of the ocean that extends back centuries or even millennia. This information is invaluable for understanding natural climate variability, for distinguishing between human-caused and natural changes, and for validating climate models. Deep-sea corals grow very slowly, adding only fractions of a millimeter per year, but their longevity means they can provide continuous records spanning timescales that are difficult to obtain from other sources. The corals stand in the darkness, patient recorders, their skeletons preserving stories of the ocean's past, waiting for someone to read them.
Scientists have long wondered why certain deep-sea organisms produce chemicals that are toxic or repellent to predators, compounds that seem energetically expensive to synthesize and maintain, yet clearly provide survival advantages in environments where predation pressure is intense despite the low population densities. These chemical defenses include toxins that paralyze or kill, bitter-tasting compounds that discourage consumption, and substances that interfere with digestion or metabolism.
Some deep-sea sponges, for example, produce powerful toxins that make them unpalatable to fish and other predators, allowing them to grow slowly and unmolested in environments where being eaten would mean the loss of decades or centuries of growth. The study of these defensive chemicals has practical applications, as many have pharmacological properties and have been investigated as potential drugs for treating cancer, bacterial infections, and other diseases. The organisms carry their defenses within them, chemical shields against a world where every encounter could be fatal.
Hidden far beneath the surface lies a network of underwater caves and tunnels, carved by water flowing through soluble rock, or created by lava flowing beneath a solidified crust. And these submerged passages can extend for kilometers, connecting different parts of the ocean floor or linking the ocean to underground aquifers. Exploring these caves is challenging and dangerous, requiring specialized equipment and training, but it reveals hidden ecosystems and geological features that are invisible from the surface. Some caves are home to unique species found nowhere else, organisms that have adapted to the stable, dark, and often isolated conditions of the cave environment. And studying these communities provides insights into evolution, speciation, and the limits of life. The caves wind through the rock, dark and narrow, filled with water that has not seen light in thousands of years, holding secrets that few will ever witness.
A few scattered locations on the seafloor emit plumes of clear fluid that is chemically distinct from seawater, containing elevated concentrations of dissolved gases, metals, or organic compounds, yet lacking the high temperatures typically associated with hydrothermal vents. Cold seeps are powered not by volcanic heat, but by geochemical reactions occurring in the subsurface. Processes like the oxidation of methane, the reduction of sulfate, or the weathering of minerals. The organisms that inhabit cold seeps are similar in some ways to those at hydrothermal vents, relying on chemosynthetic bacteria to convert chemicals into energy, but the communities can be quite different in composition and structure. Cold seeps are found in many parts of the ocean, from shallow coastal areas to the deepest trenches, and they play important roles in the global cycles of carbon and sulfur, acting as pathways for these elements to move between the solid earth and the ocean. The seeps emit their fluids quietly, without drama, their presence revealed only by the communities that gather around them and by the chemical signatures they leave in the water.
Deep below the waves, there are places where the seafloor is carpeted with xenophytophores, giant single-celled organisms that can grow to the size of grapefruits or larger, making them some of the largest single cells known to science. These strange creatures construct delicate shells, or tests, from sediment particles glued together with organic secretions, and they live by extending thread-like pseudopods through the sediment to capture bacteria and other food particles. Xenophytophores are common in some parts of the deep sea, but remain poorly understood, as they are extremely fragile and difficult to collect intact, often disintegrating when disturbed or brought to the surface. Their ecological role is uncertain, though they are thought to contribute to bioturbation, the mixing of sediment by organisms, and they may also serve as habitat or food for other deep-sea animals. The xenophytophores rest on the seafloor, enormous yet delicate, their cellular complexity hidden within their sediment shells, organisms that challenge our definitions of simple and complex.
In the dark quiet of the ocean floor, something unusual occurs when deep-sea fish exhibit sexual dimorphism so extreme that males and females were once classified as separate species, only later recognized as the same organism when specimens were examined more carefully. This is particularly striking in certain angler fishes, where the tiny males, sometimes only a few centimeters long, are dwarfed by the much larger females, which can reach sizes of 30 centimeters or more. In the most extreme cases, the male attaches himself permanently to the female, fusing with her tissues and becoming a parasitic appendage that provides sperm when needed, while the female provides all the nutrients the male requires. This bizarre reproductive strategy is thought to be an adaptation to the difficulty of finding mates in the vast, dark expanse of the deep sea, where population densities are low and encounters between individuals are rare. By fusing with a female, the male ensures that he will be present when she is ready to reproduce, eliminating the uncertainty of mate finding. The pairs drift through the darkness, inseparable, their lives intertwined in a relationship that is unique among vertebrates.
Some underwater realms reveal the presence of deep-sea fish with light organs so sophisticated that they can control not only the intensity and color of the light they produce, but also its direction and polarization, using these capabilities to communicate in a visual language that is invisible to most other organisms. These fish have arrays of photophores arranged in species-specific patterns, and they can flash them in sequences or modulate them in ways that conveys information, much like the flashing of fireflies on a summer evening. The complexity of these light displays suggests that they serve multiple functions, attracting mates, coordinating group behavior, or even conveying information about identity, status, or reproductive readiness. Deciphering this language of light is challenging, as it requires observing the fish in their natural environment, in darkness and at depth, where their behaviors can be recorded and analyzed without the distortion that captivity or artificial lighting might introduce. The fish flash and glow, speaking in light. Their message is passing through the water in patterns we are only beginning to understand.
Certain abyssal zones whisper of organisms that exhibit remarkable regenerative abilities, capable of regrowing lost limbs, organs, or even entire body sections after injury or predation, a trait that is valuable in an environment where encounters with predators are infrequent but can be devastating. Some deep-sea starfish and brittle stars can regenerate entire arms from a fragment of the central disc, and certain worms can regrow both head and tail from a separate segment, effectively cloning themselves in the process. These regenerative powers are of great interest to biologists studying tissue repair, stem cell biology, and the molecular mechanisms that control growth and differentiation, as understanding how these organisms regenerate could provide insights applicable to human medicine. The creatures heal and regrow, their bodies flexible and resilient, capable of recovering from injuries that would be fatal to less adaptable organisms. Explorers have reported traces of deep-sea woodfalls, logs and branches that have drifted out to sea and sunk to the ocean floor, where they become colonized by specialized organisms that can digest wood in the absence of oxygen, creating ecosystems that are distinct from both whale falls and hydrothermal vents, but that share some similarities with both. Woodfalls support communities of bacteria, fungi, and invertebrates that break down the cellulose and lignin in the wood, releasing nutrients and creating microhabitats within the decaying structure. Some of the organisms found at woodfalls are closely related to those at whale falls, suggesting that they share evolutionary histories, and that these two types of organic falls may serve as stepping stones for dispersal, much as whale falls connect chemosynthetic ecosystems. The wood lies on the sea floor, slowly softening and disintegrating, a piece of the terrestrial world transported into the abyss, supporting life in an unexpected place. Far below, in the crushing pressure, something mysterious unfolds when deep-sea sediments undergo diagenesis, the chemical and physical changes that transform loose sediment into solid rock over geological time.
processes that involve the precipitation of minerals, the compaction of particles, and the alteration of organic matter by heat and pressure. Diagenesis in the deep sea is influenced by the composition of the sediment, the chemistry of the pore water, and the presence of organisms that burrow through the sediment and alter its properties. These processes can create distinctive sedimentary structures, like nodules and concretions, which form when minerals precipitate around a nucleus and grow outward, and they can also preserve fossils in exquisite detail, capturing snapshots of ancient life for future geologists to discover. The sediments compact and harden, slowly becoming stone, and within them the history of the ocean is written in layers, a record that will endure long after the organisms that created it have disappeared.
There are ocean depths where the distribution of certain species seems to follow patterns that are difficult to explain based on environmental factors alone, with populations that are more closely related to distant populations than to nearby ones, suggesting complex dispersal histories influenced by past ocean conditions, currents, or geological events. These biogeographic patterns are puzzles for evolutionary biologists and ecologists who use genetic data, oceanographic models, and paleontological evidence to reconstruct the histories of species and understand how they came to occupy their current ranges. In some cases, the patterns suggest that populations were once continuous but have been fragmented by changes in ocean circulation or sea level, leaving isolated groups that have since diverged genetically. In other cases, the patterns indicate long-distance dispersal, with larvae or adults carried by currents across vast distances to colonize new habitats. The species are scattered across the ocean, their distributions shaped by history, their relationships a tangled web of ancestry and migration.
In the endless black of the abyss, there exists a phenomenon where certain deep-sea organisms enter states of dormancy or torpor during periods of food scarcity, reducing their metabolic rates to near-zero levels and effectively shutting down all non-essential functions until conditions improve. This strategy allows them to survive extended periods without feeding, conserving energy, and waiting for the next pulse of organic matter to arrive from the surface. Some organisms can remain dormant for months or even years, their bodies barely maintaining the functions necessary for life. And when food becomes available again, they rapidly rouse themselves and resume normal activity. Dormancy is a common strategy in harsh or unpredictable environments, and studying it in deep-sea organisms provides insights into the physiological and biochemical mechanisms that allow life to persist under extreme conditions. The organisms rest in stillness, almost lifeless, their existence reduced to a whisper, waiting patiently for the world to change.
Long ago, researchers detected hints of deep-sea volcanic eruptions that occur without warning, sudden outpourings of lava, or explosive releases of gas and ash that reshape the seafloor and create new habitat for colonization by pioneer species. These eruptions are difficult to detect and study, as they occur in remote locations and often leave no surface trace. But advances in seafloor monitoring, including networks of seismometers and hydrophones, have allowed scientists to detect and respond to eruptions more quickly. When a new eruption is discovered, expeditions are mounted to study the fresh lava, the chemical composition of the fluids being released, and the organisms that are beginning to colonize the new surfaces. These studies provide unique opportunities to observe ecological succession in the deep sea, the process by which bare rock is gradually transformed into a thriving ecosystem through the arrival and establishment of different species over time. The lava cools and solidifies, black and glassy, and on its surface, the first colonists arrive, bacteria that can metabolize chemicals from the rock, preparing the way for the organisms that will follow.
Drifting in the silent blue, one may encounter the strange phenomenon of bioluminescent waves, displays of light that sometimes occur when organisms are disturbed by the movement of a submersible or a current, creating brief, shimmering curtains of blue-green light that fade as quickly as they appeared. These displays are caused by dinoflagellates, tiny planktonic organisms that emit light when mechanically stimulated, a defensive response thought to startle predators or attract larger predators that will consume whatever is disturbing the dinoflagellates. In the deep sea, where dinoflagellates are less common than in surface waters, bioluminescent waves are rare but striking when they occur, and they provide a reminder of the diverse strategies organisms use to survive and avoid being eaten. The waves of light ripple through the water, ephemeral and beautiful, a fleeting glimpse of the hidden lives that fill the ocean.
Some deep-sea regions hold what appear to be fossil hydrothermal vents, ancient systems that ceased activity millions of years ago, but that have left behind mineral deposits and altered rocks that preserve evidence of the high-temperature fluids that once flowed through them. These fossil vents are valuable for understanding the history of ocean chemistry, the evolution of vent ecosystems, and the processes that form ore deposits, as many economically important mineral deposits on land are believed to have formed in ancient seafloor hydrothermal systems that were later uplifted and exposed by tectonic forces. Studying fossil vents in the deep sea allows scientists to observe these systems in their original geological context, without the complications introduced by weathering and erosion, and it provides insights into how long vent systems remain active, what causes them to shut down, and what happens to the ecosystems they supported once the fluids stop flowing. The fossil vents stand silent, their chimneys cold and crumbling, monuments to past activity, evidence that the sea floor is not static, but constantly evolving.
A few underwater realms reveal deep-sea fish that have evolved to have extremely large mouths and expandable stomachs, allowing them to consume prey larger than themselves, an adaptation that is valuable in an environment where meals are infrequent and unpredictable. These fish, including gulper eels and certain types of anglerfish, have jaws that can open to enormous angles and stomachs that can stretch to accommodate prey many times their normal body volume, allowing them to take advantage of any feeding opportunity, no matter how disproportionate the size of the prey. After consuming a large meal, these fish may not need to eat again for weeks or months, digesting slowly and extracting every bit of energy and nutrition from their catch. The evolution of such extreme feeding adaptations highlights the challenges of life in the deep sea, where the scarcity of food has driven the evolution of strategies that seem bizarre by surface standards, but that make perfect sense in the context of the environment. The fish drift with their enormous mouths agape, waiting for something to wander within reach, patient predators in a world where patience is essential.
Certain underwater canyons serve as natural traps for marine debris, accumulating plastic, metal, and other human-made materials that have drifted into the ocean and settled into the deep, creating concentrations of pollution in areas that were once pristine and untouched. The discovery of significant amounts of trash in the deepest parts of the ocean has been a sobering reminder of the extent to which human activities have impacted even the most remote environments, and it has raised concerns about the potential effects of this pollution on deep-sea organisms and ecosystems. Some organisms ingest microplastics or become entangled in larger debris, and chemicals from plastics and other pollutants can leach into the water and sediment, potentially affecting the health and reproduction of marine life.
Efforts to understand the distribution and impacts of deep-sea pollution are ongoing, and they are complicated by the difficulty of accessing these environments and the slow pace at which change occurs in the deep sea. The canyons collect and hold the debris, archives of human carelessness, reminders that no part of the ocean is beyond our reach or our responsibility.
In the dark quiet of the ocean floor, something unusual occurs when certain bacteria form biofilms, complex communities of microorganisms that attach to surfaces and secrete sticky matrices of proteins and polysaccharides, creating structures that can persist for years and that alter the chemistry and ecology of the surfaces they cover. Biofilms are found on rocks, shells, shipwrecks, and any other hard substrate in the deep sea, and they play important roles in nutrient cycling, mineral formation, and the colonization of surfaces by other organisms. The bacteria within biofilms can communicate with each other through chemical signals, coordinating their behavior and creating microenvironments that are distinct from the surrounding water. Biofilms can also protect bacteria from harsh conditions, including extreme pH, temperature, or chemical exposures, and they are of interest to researchers studying microbial ecology, biofouling, and the origins of multicellularity. The biofilms coat the surfaces, invisible films of life, transforming inert material into living landscapes.
Hidden far beneath the surface lies evidence of ancient ocean basins that have closed and vanished, consumed by subduction as tectonic plates converged and one was forced beneath the other, carrying with it the sea floor, the sediments, and the history they contained. These lost oceans can be reconstructed using geological and geophysical data, piecing together fragments of oceanic crust that have been thrust onto land, trapped in mountain ranges, or found as exotic blocks in sedimentary rocks. Studying these remnants allows scientists to understand the long-term evolution of Earth's surface, the opening and closing of ocean basins over hundreds of millions of years, and the forces that drive plate tectonics. The vanished oceans are gone, their waters drained away or absorbed into the mantle, their floors melted and recycled, but traces remain, clues written in stone, stories of worlds that no longer exist.
Deep below the waves, there are places where the seafloor emits faint acoustic signals, low-frequency sounds that are not loud enough to be heard by human ears, but that can be detected by sensitive instruments, and whose sources are not entirely understood. These sounds might be produced by the slow movement of sediment, by the release of trapped gases, by the cracking of minerals under pressure, or by biological processes involving organisms too small or too quiet to be observed directly. The ocean is never truly silent. It is filled with sounds from countless sources, and disentangling these sounds and identifying their origins is a challenge that requires patience, sophisticated equipment, and a deep understanding of both physics and biology. The signals propagate through the water and the sediment, faint whispers in the darkness, evidence of activity and change that continues unseen and mostly unheard.
And so we have drifted through the deep, through realms of pressure and cold, through darkness punctuated by flashes of light, through ecosystems built on chemistry rather than sunlight, through landscapes shaped by forces both ancient and immediate. The ocean is vast, far vaster than any of us can truly comprehend, and it holds mysteries that we have only begun to uncover, questions that will occupy researchers for generations to come, wonders that will continue to surprise and inspire those patient enough to explore them. The deep sea reminds us of how much we do not know,
of how small we are in the face of the planet's immensity, and of how much remains to be discovered in the quiet, dark places of the world. It is a realm that does not yield its secrets easily, that demands respect and humility, and that rewards careful observation with glimpses of beauty and strangeness beyond imagination. If you enjoyed this gentle exploration, I invite you to like, subscribe, or share a thought below. Your support helps others find their way here, one sleepy soul at a time, and it allows us to continue these quiet journeys into the unknown, these meditations on mystery and wonder. For now, allow your breath to steady. Let the quiet of the deep ocean surround you, and let the last currents of wakefulness drift away. May you rest in the darkness, cradled by the immensity of the sea, safe and peaceful in the knowledge that the world is full of marvels, and that some mysteries are content to remain mysteries, waiting patiently in the depths for those who will one day seek them out. Good night.